Okay, so to start Chapter 8, we're going to talk about something that is actually applicable in Algebra 2 for sure, and that's trigonometry. We will get to that after the first few lessons, but the first lesson we talk about today is something called the Pythagorean Theorem, and it has to deal with only right triangles. And what it states is that the legs, when squared and added together, are equal to the hypotenuse squared of a right triangle. The legs are interchangeable. And what I mean by that is it doesn't matter which leg is A, which leg is B. It does matter, however, where the hypotenuse is. The hypotenuse is always opposite from the right angle in a right triangle. The hypotenuse is always the longest side of a right triangle. So that's the one thing that is definitely the same every time. C is always the hypotenuse. A and B can be interchanged. So in example 1, finding the length of the hypotenuse, you could say that, A is 6, B is 8. It doesn't matter if A is 8 and B is 6. And then we'd say C is our hypotenuse, which is x. So to set this up, I would do 6 squared plus 8 squared equals hypotenuse squared, x squared. This would be 36 plus 64, 6 squared plus 8 squared, which is 100, is x squared. The square root of that is the solution to this example. So the square root of 100 is 10. So x is just 10. That's it. For part B, a squared plus b squared equals c squared. 16 and 30, again, doesn't matter if it's 16 squared plus 30 squared, 30 squared plus 16 squared. That doesn't matter. And this one I'm going to have to take a second to use my calculator for because I don't remember what this one was. 16 squared plus 30 squared is 1156 equals x squared. To solve this for x, I have to take the square root of 1156, and that is 34. Okay, 34. For part C, finding the length of this hypotenuse, we would take 65 squared plus 72 squared equals x squared. So 65 squared plus 72 squared is 9409 equals our hypotenuse squared. I take the square root of 9409, and that is 97. So all of these happen to be just nice numbers, easy to find, just meant for us to understand the formula. The legs squared and added together are equal to the hypotenuse squared. Okay, so that's finding the hypotenuse. Now, that's not always going to be the case. Sometimes we're going to have to find a leg. So you can decide if that leg you're finding is always A or always B, but there's a common thread with each of these examples. If I'm doing a squared plus b squared equals c squared, I'm just going to write it like this. X squared plus 4 squared equals 7 squared, because 4 and x are the legs. So that becomes x squared plus 16 equals 49. Okay, just simplifying. So that's going to be x squared equals 49 minus 16, which is 33. The solution to this, x equals the square root of 33. To be honest, right now, I'm good with you leaving it like that because we can't, if we remember from our last lessons, we can't simplify the square root of 33. There are no perfect squares that are factors of 33. Now, if I were rounding this, if I ever ask you to round, you would round to 1 decimal place. If I were rounding, this would be 5.7. That's just me punching it into the calculator. So really the only difference is finding a leg, you're taking the hypotenuse squared minus a leg squared to get the other leg. So in part B, same idea, x squared plus 16 squared equals 19 squared. So x squared plus 16 squared, which is 256, equals 19 squared, which is 361. So x squared equals 361 minus 256, which is 105. And 105 is another one of those square roots we can't simplify. So I would just leave it as the square root of 105. Now, if I did ask you to round to the nearest tenth, this would be about 10.2, okay? So this would be a nice spot for you to stop, pause the video, and work through part C on your own. When you're ready to move ahead, resume the video, and then we'll cover some examples where you're finding a distance, having to draw a picture, okay? So pause the video. When you're ready to move ahead, I'll show you the answer. So just because I'm a mean guy, I gave you one that is a square root that could be simplified, because there is a perfect square that is a factor of 75, 25. 25 and 3 are factors of 75. So if I were simplifying this, it would be 5 square root 3 as my answer. Now, we will get some practice on this, but simplifying those square roots is not going away, because in the next lesson we are going to be using square roots. So I want you to be comfortable working with square roots in different ways. Now, example 3, we are finding a distance, which really just means we have to determine whether we're finding a leg or a hypotenuse. That's really the only two possibilities with these right triangles. Now, these, you're going to have to draw a diagram to help you understand them. When we measure computer monitors or TVs, when we say it's a 55-inch TV, it's not how wide it is, it's how long the diagonal is of that object. So a computer monitor is a rectangle. You want to buy a 19-inch monitor that has a height of 11 inches. So if it has a height of 11 inches, that's going to be the height. The 19-inch monitor, the 19 inches, is this distance right here, the diagonal. And that creates two right triangles. And we're asking, what is the width of the monitor, of a 19-inch monitor? So the width is this value right here, this horizontal length. So to find this, we're given the hypotenuse, we're given one of the legs, so we are finding the other leg. Now, in examples like this, I really would like you to round, because we are finding a measurement that we would use in an everyday situation. So if I'm going to find a value here, 361 minus 121, 240, I'm going to take the square root of 240, and I'm going to round it. So I'm going to use these little squiggly lines to show it's about this much. It's about 15.5 inches wide. So that's an approximation. We round it. I rounded there. So that's what I mean by approximating or rounding. In context problems, definitely round. Don't simplify. Round. Punch it into your calculator, get a number. That's the length, or that's the width. So in example 3, I want you to get practice drawing an example out and then working through it. And I know this is getting a little long, but we have a couple more examples to cover on the back. So pause the video, work through this, and then we'll kind of push ahead. Okay, so our last couple examples have to do with the flip side of the Pythagorean theorem. So before we said, if a triangle is a right triangle, then a squared plus b squared equals c squared. Now all we're saying, we're flipping that statement around, it's the converse. We're saying if a squared plus b squared equals c squared in any triangle, then that means that triangle has to be a right triangle. So we are going to try to prove whether a triangle is right or not right. So in example 4, like I said before, we're trying to pick A, B, and C in these three sides. So if this were a right triangle, 13 and 84 would be the legs. 85 would have to be the hypotenuse because it's the longest side. So I'm going to test 13 squared plus 84 squared. Is it equal to 85 squared? So it's real quick. 13 squared plus 84 squared in my calculator is 7225. 85 squared in my calculator is 7225. So all that means is this triangle has to be a right triangle. So my answer to this question is yes, and that's because the sides satisfy the Pythagorean theorem. Okay, so it's just, I should capitalize theorem. It's just seeing if a squared plus b squared equals c squared. If it's true, the triangle is definitely a right triangle. If it's not true, it's something else. It might still be a triangle, but it's not a right triangle. So pause the video, work through guided practice number 4, and then we'll cover the last example of this lesson. Okay, so for this example, a squared plus b squared does not equal c squared, so this is not a right triangle. However, this is a triangle, and it's actually what we would call an acute triangle, which means all 3 angles are less than 90 degrees. So this is an acute triangle. And I'm just going to go into a little bit of depth about what that means. So whether to tell if a triangle is obtuse or acute when we know that it's not a right triangle. So basically, if we do a squared plus b squared equals c squared, and the legs, when squared and added together, are less than the hypotenuse, then it's obtuse, because c squared is bigger than a squared plus b squared. Okay, that's when it's obtuse. If a triangle is acute, that means that c squared is smaller than a squared plus b squared. So the way I remember this is that for it to be acute, c squared is small, all right? The biggest side is smaller than the other 2 sides when squared and added together, okay? So I should explain that better. A squared plus b squared equals c squared, it's perfectly a right triangle. If c squared is bigger than a squared plus b squared, it's got to be obtuse. And I think of the word bigger and obtuse, I associate those as being bigger than 90. You know, obtuse is bigger than 90. Acute is smaller than 90, so c squared is smaller than a squared plus b squared. So I want to show a concrete example of that. In example 5, we're going to test if this triangle is acute, obtuse, or right. So I'm going to do a squared plus b squared equals c squared. And that, I'm not making that statement that yes it is. I'm saying is it. I'm testing if it is. 6 squared plus 11 squared is 157. Okay? Is that equal to, and I'm not going to put an equal sign there, is that equal to 14 squared? No, it is not. It is smaller. So going back to what I said before, c squared is bigger. C squared is bigger. So this triangle is obtuse. And that's because c squared is greater than a squared plus b squared. Okay? So that part's a little bit tricky. I'm going to give you some practice on that to get you used to those types of problems. But that's how we classify triangles using that Pythagorean theorem. So equals is just right. They're equal. When c squared is bigger, it's an obtuse triangle. When c squared is smaller, it's an acute triangle. So like I said, you're going to get some practice to dial this in, and then we can go through examples. I can go through questions on Friday when we're back together in class.